Welcome back, guys. So now we're going to learn about arrays. So what is an array? An array allows you to define a variable with a given name, but have it so it can store multiple of the same type. So it's best I show you this in code so you can see it clearly. Let's say I wanted to take a name at some point in time from my user. Well, what I would do is I would create a character array for the name, and in here goes the length. So char name 20 with these brackets as well. So what that means is a name variable that has a type of char, so it can only store 1 byte at a time, and we want it to have 20 bytes. So in other words, we can store 20 bytes in this name variable. So how does that work then if char can only store 1 byte? Well, what happens is the compiler looks at the data type, it sees it's a char, so it knows it's 1 byte. Then it sees this number and it knows that we want to have 20 of them. And it also knows we want it to be able to be referenced by the same name, since char name. So it allows us to access 20 bytes using the same name. So how do you access them then? Well, like this. Let's say we wanted to set name to A like we did in previous tutorials. You can see a syntax error. Why? Because this is an array. We can't set it like this. So if we did name 0 equals A, that works fine. So what's happened here then is we set the first byte in our name array to 0. Because in C, indexes start from 0 and you access indexes in arrays. So in this case, what we're doing, we're accessing index 0 from the name array and we're setting it to A. So you could do the same here. 1 equals B. Name 2 equals C. And now if you wanted to output that, you could go printf C for char, and then we go here and we go name 0. So what that'll do, that'll output A. If we put a 1 here, it would output B. If we put a 2 here, it would output C. Now, there's rules for these indexes. Firstly, they can't be negative. Secondly, indexes always start from 0. In other words, if I wanted to access byte 1 of this name array, I would use 0. The third rule is, always the fourth, you cannot exceed this length. Say I want to access the last byte of this array. Would I do name 20? Absolutely not. I would do name 19 because they start from 0. When we access it, we always start from 0. So name 19 equals D would set the last byte of this array to D. Now, in most languages like Java and stuff like that, if you exceed the buffer is another word for array, by the way. If you exceed it, what will happen is it'll throw some sort of exception and your program will gracefully end. In C, it doesn't work like that. In C, if you exceed this buffer, at best case scenario, your program will crash. Worst case scenario, a hacker could use this to their advantage. And it really is that serious. Because in C, when it's compiled, there's a bunch of return addresses and stuff like that stored on the stack. And right now we store this array on the stack. How the stack works is when you enter a function, it allocates some room on the stack for all the bytes that are in this scope. And the scope is anything between these brackets. That's what a scope is. So in our case, it will allocate 20 bytes on the stack for us. And it'll also allocate some bytes for these variables here for our function prototype. Now, the stack memory is allocated by simply decrementing the base pointer or stack pointer. And the problem with that is you can also run out of space very easily, because we're not asking the operating system for to give us some data here. We're not doing that. What we're doing is we already have the data, and we're just literally just moving the pointer down 24, 28 bytes, and that's what we're doing. And then that gives us room to set these things. So what happens is when you leave the function, it resets the pointer back to where it was. And now once it does that, everything here gets naturally freed. And when I say freed, I don't mean deleted. It's just kind of like it ends up in a kind of like undefined state, and it can be overwritten by other function calls and stuff like that. But you don't need to worry too much about that. That's quite a complicated subject. But the point is I'm trying to make is you have to be careful how much you allocate on the stack, because the stack can only take so much. And secondly, back to our potential problem where if you go over this buffer, an experienced hacker could offset this just right to overwrite the return address that will be on the stack. And what the return address does is it basically holds the address to the last function that called you. So then when this function finishes, it'll pull that address and go back to where it was executing. And the problem with that is a hacker, experienced hacker, could overflow this buffer. It's called a buffer overflow. You're welcome to look it up. And when they overflow it, they could overwrite that address to point to somewhere else. And that's why it's very dangerous. So in C, you always have to make sure you check that anything you're accessing here can fit. So for example, let's say I had an integer I equals 50, and I did name I equals E. So what will happen is it would go into I, it would pull 50, and it would set index 50. But the problem here is we can only store 20 bytes. So what happens is it'll crash the program. But experienced hacker could change that and do nasty things. So how you get around that is you can basically check that I can fit into here, and if it can't, then you don't set it. But anyway, more to conditions later on. Just wanted to get that out there. So what we can do now then is we can test this. So get rid of name 19 if you did that, because that'll crash the program, right? And we're going to open up command prompt, cmd, and I'm going to copy and paste this address by going cd, and we're going to right click, enter. And now you're going to go gcc main.c -o main, and that should compile fine. Do main now, and you can see that it outputs C, because we're outputting element 2 in the array, which is C. So that's how arrays work. It allows you to access the same variable name and multiple bytes. So that's literally all it is. So basically, rather than having 20 different variables named name 1, name 2, name 3, name 4, name 5, you can just do name and then do 20, and it really is that simple, and it's very efficient as well. Like, you can access these in a number of different ways, like such as using loops. Without arrays, the language wouldn't really work very well. So that's what arrays are, and basically that is it for arrays. You can have arrays of all different types. I could have an integer array, for example, integer abc 30. So now I've declared 30 integers, and I can go abc 0 equals 55, abc 1 equals 22. So that is what arrays are. A very, very handy feature of the language, and you can see why.